Hello, I'm Professor Von Schmohawk, and welcome to YU. In our lecture on the decimal number system, we saw that decimal numbers can represent fractional quantities by adding a decimal point to the right of the ones digit, followed by any number of digits. Multiplying a decimal number by 10, which can also be written as 10 to the first power, increases the value of each digit by a factor of 10, shifting the digits one column to the left. Likewise, multiplying a decimal number by 1/10, which can also be written as 10 to the negative first power, decreases the value of each digit by a factor of 10, shifting the digits one column to the right. The net effect is that the decimal point moves. For example, if we multiply a number times 10 to the second power, the decimal point moves 2 columns to the right. Or, if we multiply a number by 10 to the negative fifth power, the decimal point moves 5 columns to the left. Shifting the decimal point by multiplying by some power of 10 is used by engineers and scientists to write numbers in a format called scientific notation. Many years ago, units of measurement such as feet, meters, miles, seconds, pounds, and so forth were chosen to describe things on a human scale. Things which we encounter in our everyday lives can usually be expressed in these units without needing gigantic numbers or tiny fractions. However, science and technology have expanded the range of our measurable universe far beyond the human scale. Today we must work with numbers vastly larger than anything the Romans had to deal with. For instance, the distance to the nearest star is 25 trillion miles. The number of atoms of gas in a toy balloon is about 500 sextillion. And the size of one of those atoms is about 1/10,000,000,000th of a meter. Hundreds of years ago, time measurements much smaller than a second would have been difficult or impossible. Today, engineers and physicists routinely work with measurements of tiny fractions of a second. In fact, we now have names for these units like millisecond, microsecond, nanosecond, picosecond, femtosecond, attosecond, zeptosecond, and yoctosecond. Unfortunately, numbers with lots of zeros can become confusing and hard to work with. This is why scientific notation was invented. Numbers written in scientific notation consist of two parts. The first part, which can be positive or negative, is written as a single digit, which can optionally be followed by a decimal point and one or more additional digits. The second part is a multiplier for the first part. This multiplier is always written as 10 with an integer exponent. Since the exponent can be positive or negative, the multiplier can make the number as large or small as we like. For instance, the distance to the nearest star, 25 trillion miles, expressed in scientific notation is 2.5 times 10 to the 13th miles. And the number of atoms of gas in a toy balloon, about 500 sextillion, expressed in scientific notation is 5 times 10 to the 23rd. Very small numbers are also much easier to express in scientific notation. For example, the size of an atom of helium, about 1/10,000,000th of a meter, expressed in scientific notation is 1 times 10 to the negative 10 meters. And 1 yoctosecond is 1 times 10 to the negative 24 seconds. To convert a number written in scientific notation to a standard decimal number, we simply multiply the first part times the second part. This moves the decimal point to the proper position in the number. If the exponent of the multiplier is 0, the decimal point does not move, since multiplying by 10 to the 0 power is the same as multiplying by 1. If the exponent of the multiplier is positive, the decimal point is moved that many columns to the right. If the decimal point must move beyond the last digit, zeros are added to the end of the number to accommodate its new position. If the exponent is negative, the decimal point is moved that many columns to the left. If the decimal point must move beyond the first digit, zeros are added to the beginning of the number to accommodate its new position. Now that we have seen how to convert a number written in scientific notation to a standard decimal number, let's convert a decimal number into scientific notation. We'll start by adding a multiplier of 10 to the 0 power. This is the same as multiplying by 1, so the value of the number is unchanged. For a number to be written in scientific notation, the decimal point must be positioned immediately after the first non-zero digit of the number. In this example, we will need to move the decimal point 3 columns to the left. For each column we move the decimal point, we must increase the exponent of the multiplier to compensate for the fact that we have decreased the value of the number by 1/10. The number's value is unchanged, and it is now written in scientific notation. Let's try writing the number 1 billion in scientific notation. Once again, we'll add a multiplier of 10 to the 0 power. Now, to position the decimal point after the first non-zero digit, we will need to move it 9 columns to the left. Therefore, we must increase the exponent of the multiplier by 9. The number is now written in scientific notation. For our final example, let's convert a very small decimal number to scientific notation. We add a multiplier of 10 to the 0 power. To reposition the decimal point after the first non-zero digit, we will need to move it 7 columns to the right. Therefore, we must decrease the exponent of the multiplier by 7. The number is now written in scientific notation. As we have seen, exponents can be very useful, enabling us to write very large and very small numbers in a much more compact fashion. In the next lecture, we will see how to create and simplify mathematical expressions which contain exponents.